A strange truth about megaprojects is that engineering is rarely the limiting factor. Coordination is. The hardest part is keeping truth, incentives, and responsibility intact for decades. We already know how to build at striking scale. Case reports describe long-span civic structures and landmark forms that cross into megastructure practice. A lightweight 100-meter span dome in Manila is one example. The Great Mosque of Algiers is another, where the project did not just finish a building. It helped shape an entire new city district around it. Those examples matter because they show what megastructure means in practice. It is not only big concrete and steel. It is a built system that spills into transport, utilities, public space, and long-term operations. Once a project becomes a district anchor, the boundary is no longer the envelope. The boundary becomes governance. That leads to the first high-impact finding. At extreme scale, design becomes systems engineering across disciplines that do not share a single verification workflow. Structure, heat, moisture, facade, behavior, and operational wear interact over long durations. A 2025 research direction points to coupled analysis using thermal skin heat transfer simulation, aimed at verifying large building skins as integrated systems. The upside is better prediction. The downside is new opacity, where decisions depend on chained models that few people can audit. So the question shifts from, can we simulate it, to, can we govern the simulation? Leaders have to decide which models are decision support, which are compliance evidence, and which will later steer operations. Versioning, validation scope, calibration data, and accountable sign-off stop being paperwork. They become safety features. The second finding is more financial than technical. Life cycle and embodied impact accounting is moving from retrospective reporting into the design loop. In 2025, expert synthesis on data-driven lifecycle assessment frameworks for modular facades treated environmental accounting as a data and design system problem. That hints at where procurement is headed. When impact accounting is data-driven, it can be scored, traced, and enforced through supply chains, but only if the record is real. Audit-grade as-built records, supplier declarations, testing data, inspection logs, and maintenance histories have to be treated as core infrastructure. Without that lineage, carbon claims, durability claims, and even replacement planning become narratives. Narratives are expensive to maintain and cheap to abuse. A third finding comes from the subsurface, where humility is still mandatory. Deep excavation and tunnel construction are mature disciplines, with modern techniques formalized long ago. But every tunnel is bounded by geology and by the uncertainty tails that geology creates. Monitoring and stage construction are well developed. What still breaks budgets and schedules is the mismatch between what was assumed and what was found. That makes geotechnical transparency a board-level risk policy issue, not a field detail. Ground condition assumptions, investigation limits, contingency triggers, and decision rights for stoppage or redesign should be explicit before contracts harden. Change order governance should separate foreseeable uncertainty from truly new conditions. Otherwise, the subsurface becomes a financial instrument, not an engineering domain. The fourth finding operates at the scale of continents. Kilometer-resolution Continental-Scale climate simulation is now a planning-relevant capability for stress-testing infrastructure boundary conditions. That matters because water, heat, flood risk, and storm exposure do not respect political boundaries or agency charts. The models can speak in the language of corridors, basins, and regions, but delivery remains fragmented. Transport is planned in one place, water in another, energy somewhere else, settlement patterns somewhere else again. The geography is coupled. The institutions are not, so adoption will likely lag model availability, and the biggest danger is false precision. A single model run can be treated as destiny when it should be treated as a scenario band that triggers adaptation choices. Now, for the most counterintuitive bridge to the future. Some of the most useful thinking about Earth megaprojects is being sharpened by off-world construction research. In 2024, quantitative evaluation of lunar in situ large-scale construction compared regolith solidification techniques for building with local materials. That is not just about the moon. It forces logistics realism. If you can only use what you have, you learn to design for scarcity, autonomy, and repairability. Those constraints map back to Earth in polar sites, disaster zones, islands and deserts, subsea support nodes, remote mines, and off-grid industrial plants. The transferable insight is not a specific recipe for regolith. It is the discipline of designing around constrained supply chains, limited human access, and high penalties for failure. Across all these findings, one theme keeps repeating. Megastructures fail less often from missing technology and more often from missing custody. Custody of data. Custody of maintenance funding.